sometimes you're given a definite integral in which you have to simplify it before you can actually take the antiderivative, just like we saw with indefinite integrals or regular antiderivatives. If we take a look at example number 5, we have x squared minus 9 over x minus 3 in our integrand. All right, now that we have no basic rule for, but the keen eye is noticing that we see x squared minus 9, and that's a situation of the difference of two squares. So if we factor our numerator, we have x minus 3 times x plus 3, and that eliminates our x minus 3. So we do have an issue with our domain at x equals 3. However, we're only interested in the function from x equals 1 to x equals 2. So our domain issue is not a part of the interval on which we're taking our integral. So our function is continuous, and therefore we can proceed with the rest of the fundamental theorem of calculus. So this, even though it was originally x squared minus 9 over x minus 3, actually is behaving like the integral from 1 to 2 of x plus 3 dx. That's a nice, easy antiderivative to take care of. That's going to become x squared over 2 plus 3x, evaluated from 1 to 2. So we're going to need to plug 2 in first. So we have 2 squared over 2 minus 3 times 2. I'm going to wrap that in parentheses, minus 1 squared over 2 plus 3 times 1. That also gets set in parentheses, as I mentioned before. Now again, this is a correct answer. We can simplify it slightly. We have 4 over 2, which is 2, minus 3 times 2, which is 6. So we have 2 minus 6 there. And then we are subtracting, and we have a half plus 3, so that's 3.5. And so we have negative 4 minus 3.5, so negative 7.5 will give us our solution. Okay. In terms of piecewise defined functions, we want to be prepared for those as well. Well, let's say that f is equal to 3 if x is less than 1, and equal to 2x plus 1 if x is greater than 1. And you know what? I'm going to change my bounds here on the fly. We're going to change that to a 0. There we go. All right, now things are better. So our function needs to be continuous, and in fact it is, because when x is 1, if we plug 1 in here, we have 3. So 3 from both ends, so therefore our function follows the 3 rules for continuity, and therefore we can find our integral from 0 to 4. So how do we go about doing this? Well, we have two different parts to f. So we have one part for 0 to 1, which is 3, and then we have another part from 1 to 4, which is 2x plus 1. We have to split this up into two integrals. What we're looking at here is the integral from 0 to 1 of the function that belongs to f prior to 1. And then we're going to add to that the integral from 1 to our upper bound. And again, we're allowed to do that because 0 to 1, so we pick up where 1 and we go all the way to 4. And this will be 2x plus 1 dx. All right, so now it's twice the solving pleasure. 3's antiderivative. I can't fit down there. Good. Okay. So 3's antiderivative is 3x, and that's evaluated from 0 to 1. And then 2x plus 1's antiderivative is x squared plus x, and that's evaluated from 1 to 4. All right, so we'll move this up here, give you a little more space from the bottom of the screen. This will become 3 times 1 minus 3 times 0. All right. And we're going to add to that, and now we're going to plug in 4 first. So we have 4 squared plus 4, and we're going to subtract 1 squared plus 1. All right, and that is all being grouped together as well. So what do we have here? We have 3 minus 0. And then we have 16 plus 4, which is 20, minus 2. So we end up having 3 plus 18 for a final answer of 21. So piecewise defined functions can be integrated as well. We can do definite integrals with those. Again, we're just making sure that we have the function being continuous. And again, wherever our condition changes, that's where our upper and lower bounds of our two minor or partial integrals will have for their bounds.